Assalamu alaikum wa rahmatullahi wa barakatuh, and a very good afternoon to all viewers. It is a great pleasure to welcome all viewers to the 12th series of Research and Innovation webinar, School of Electrical Engineering. My name is Shari, the moderator for today's session. This program is brought to you live from School of Electrical Engineering, Faculty of Engineering, University Technologies Malaysia's Facebook. Without further ado, I would like to invite Professor Dr. Muhammad Kamal Ibrahim, the Associate Chair of Research and Academic Staff, to give a short opening, as well as introduce our guest speaker, Professor Dr. Muhammad Fua'ad Rahmat, the Head of Process Tomography and Instrumentation Research Group. Over to you, Prof.
Thank you, Puan Sherry, for introducing this event. Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera to all viewers. Thank you to all viewers for watching our webinar series brought to you live from FP School of Electrical Engineering, Faculty of Engineering, University of Malaysia. Today, our speaker is Professor Dr. Muhammad Fua'ad Rahmat, which is the head of our Process Tomography and Instrumentation Research Group. He will be talking on the current research in sensors and actuators applied in instrumentation system. Before he gave his presentation, I would like to introduce Prof. Dr. Muhammad Fua'ad Rahmat. Prof. Muhammad Fua'ad Rahmat received his first Bachelor Engineering degree in Electrical Engineering from University Technology Malaysia in 1989. He then received MNC Master in Control System from the University of Sheffield, UK in 1992. And PhD in Instrumentation Engineering from Sheffield Hallam University, UK in 1996, respectively. He is an active senior member of IEEE and currently holds positions as Deputy Chair of IEEE Control System Society Malaysia Chapter. He was appointed as the head of Department of Off-Campus Program from 1998 till 2008. He is the head of Department Control Instrumentation from 2011 till 2013 and the postgraduate manager taught course in 2014 at the Faculty of Electrical Engineering. He was the Dean of UTM Space from 2015 till 2018. Currently, he is a professor in the School of Electrical Engineering and the head of Process Tomography and Instrumentation Research Group. His research interests include process tomography, system identifications and estimation, control design, signal processing, and artificial intelligence. This webinar will introduce the members and research activities of the Process Tomography and Instrumentation Research Group. In addition to that, there will be a brief introduction to other relevant research and opportunity for postgraduate study in this webinar. Now, I would like to invite Professor Dr. Muhammad Fua'ad Rahmat to give his webinar. Over to you, Prof.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Very good afternoon. Thank you, Professor Kamal, Associate Chair of Research in the School of Electrical Engineering. Thank you, Puan Sherry, for the Master of Ceremony for this event today. So my name is Muhammad Fua'ad Rahmat. I am the head of the PROTOM-i Research Group, School of Electrical Engineering. Today I will present sharing sessions on the current research in sensors and actuators applied in instrumentation system. So basically my presentation consists of 4 parts. The first part will be on the introduction. The second part will be on the process tomography system. Part 3 is on the system identification and estimation, and part 4 is the other relevant research and opportunities for the postgraduate research students. So first of all, let me give an introduction. What is sensors, what is actuators, and what is instrumentation system. So basically, sensors is a device that have capable to detect physical signals, any physical signals around us, and convert these physical signals to electrical signals which is known as voltage and current. And frequently, this sensors is always used associated with other electronics part, for example, in the signal conditioning circuit. So actuators is different from the sensors in the sense of actuator is a component of a machine that is responsible for moving and control mechanism or system. Okay, for example, if we have a, let's say, a pneumatic actuator system, so this pneumatic actuator system receive electrical signals as the input and convert this signal into a mechanical movement or motions. An actuator requires a control signal and a source of energy in order to operate. So instrumentation system, basically most of the books that I read is a collections of instruments used to measure, used to monitor, and to control a process. Basically, we measured the physical signals on the left-hand side, quantity to be measured, and then this will be sensed by the sensors. And the sensors, as we know, we have two parts of sensors, which is active sensors and passive sensors. So passive sensors is the sensors that need power supply in order to do the conversion from the physical signals to the electrical signals, while active sensors no need power supply, no need DC supply, and it has its own energy in order to convert the physical signal to the electrical signals. And then these electrical signals will be convert in terms of amplifications, in terms of rectifications, in terms of filtering, and so on. And this variable will be manipulated, okay, and transmit to the computer for further processings, either for control, for display, and so on. So today I will talk about some activities in the research in our group, which is PROTOM-i. PROTOM-i is the short form of Process Tomography and Instrumentations. So the backbone of this group actually is the Process Tomography System research. Okay, that's why it is in the middle. And then support pillars consist of 6 support pillars from other researchers as well, which is the system identification and estimations, MEMS, microelectromechanical system, control and automations, microfluidics, signal processing, and artificial intelligence and optimizations. Okay, so today I'm going to talk about the process tomography systems and on the system ID and estimations, and the rest of the part I will share with other researchers in my group. So this is the process tomography and instrumentation research group members. We are consist of 17 members. Okay, so for those in the School of Electrical Engineering, so this is familiar with them. Okay, 17 members in the PROTOM-i research group, and our strength is shown here, where we have 2 professors, 4 associate professors, 8 senior lecturers, 2 lecturers, and 1 research officer. So the strength of our group also indicated by our publications strength, where the H-index corpus varying from 1 to 24, okay, as listed in this slide. So that is the part 1 of my presentation. So I will go on the part 2, research in the process tomography, which is the backbone of the research group PROTOM-i. So as if you go to the Wikipedia or the dictionary, tomography is the combination of 2 words, which is tomo and graph, where is a slice of picture, okay, that represent flow in the pipe. So as we know that in industrial pipe, we consist of liquid, consists of gas, consists of solids that flow inside the pipe. So engineers need to design tomographic measurement system in order to monitor the flow of the gas, of the liquid, of the solids, okay, inside the pipe by using a sensors that circulate around the pipe. Okay, so is obtaining a plane of section image which shows slice through an object. We don't have to break the pipe. Okay, we can monitor the pipe by using the sensors, which can give signals from the flow, and then these signals will be manipulated by the image reconstruction algorithm for display in the computer. So why process tomography is important? Okay, so for measurement of flow in the clean liquids and fluids, we have a wide choice of instrumentation. So, however, if the process contains two components, for example, solids and gas, or maybe solid and liquid, or maybe three components, oil, gas, and water, which cannot mix together, so that will be a problem for engineers to monitor the flow of that particular in the pipe. Okay, so knowledge is what happened within the mixing vessels, and similar process vessels is important in improving manufacturing efficiency. Okay, give a potential good solutions for this type of problem is to use process tomography, which is cheaper, which is safe in order to monitor the process pipe. Moreover, if we go to the chemical engineering plant or chemical mixer, process tomography is required, especially on the bioreactors and oleochemicals process for internal process observations. Okay, in order to monitor the mixing and gas transfer in reactors, in order to improve product quality and to save the plant operational for cost and smart energy management system. That's why we need process tomography in helping the researcher, in helping the engineers for benefits of the process. So, in overview, okay, tomography is, I can say is an open loop system where you measure the signals from the sensors, and then these sensors will be go to the signal processing or signal conditionings, and then it will go to the image reconstruction algorithm, and then will be displayed in the computer. So that's why we need sensors mounted around the pipe, okay, and we have to do some mapping, okay, the inverse problems and the forward problems, okay. Forward problem is to simulate the particles or the solid part moving in the pipe, okay, as shown in the figure here, and then we arrange the sensor in such a way that it around the pipe, okay, and the numbers must be as close as possible in order to produce a higher resolutions and to produce a good image at the end. So basically, tomography sensors consist of two parts, which is the hard field and the soft field. So hard field is set up an uniform narrow field for which the sensitivity is independent of the parameter distribution inside the sensor. So optical tomography, positron, X-ray, gamma ray, all are considered as hard field. The second one is the soft field, where we generate inhomogeneous field, and the sensitivity distribution inside the field depends on the parameter distributions, which is, I can say, use a low current, which is example of it is electrical capacitance tomography, electrical impedance tomography, and etc. So the block diagram of the process tomography, as I say, is an open loop system. So it consists of industrial pipeline, and the sensors mechanism can vary, okay, whether you are using optical, capacitance, resistance, impedance, electrical charge, and so on. And then this sensor will detect the physical signals inside the pipe, and then convert to the voltage or current. And this voltage or current will go to the second phase, which is a signal conditioning. So in signal conditioning, it consists of the pre-amplifications, amplifier, rectifier, low pass filter, and so on, in order to improve the signals that bring the information and it goes to the data acquisition system. It goes to the image reconstruction algorithms. So most of the research in process tomography, the significant contribution is more towards the image reconstruction algorithm. How we're going to manipulate the voltage and the current information that we obtain from the measurement to construct the nearest, the accurate image that represent in the slice of the pie. And this will be useful for inspections, for concentration determinations, for velocity measurements, for mass flow rate measurements, environmental monitoring, flow measurement, or identifications of the flow pattern inside the plant. So it consists of three main things, which is the array of the sensors, the signal conditionings, and the host computer, which is responsible to collect and process the data. So basically, the industrial process tomography come in the early 1990s and late 1980s due to the fact that tomography has been successfully implemented in the medical tomography, which is all the doctors using a scanner, okay, body scanning in order to detect the problems of the human, okay, basically on the head, on the leg, and so on. So he's using a X-ray, okay, as shown in the slide. But as you know that X-ray have its own disadvantage because X-ray cannot detect soft tissues like discs between the lumbar, okay, and other things, brain and so on. So this disadvantage of the X-ray scanning is covered by the medical tomography name is a MRI or magnetic resonance imaging. Okay, nowadays if people have for example a slip disc problem, okay, they're having lower back pain, okay, and the leg pain. This is due to the spine of that human is not in the good conditions, okay, and this can be detected by using MRI, where MRI is able to detect the soft tissues inside the human body. So this is some of the examples that MRI can do for brain, for knee, for cancer, for depression, and for the sleep disc detections. So we have discussed previously the industrial process tomography and the medical tomography. So what is the major difference between these two? Basically is the time scale, okay? And the time scale and the data collected in order to reconstruct the image. So medical methods can often take several tens of minutes to obtain a set of results consisting of many views and many projections from which the tomogram may be obtained. But in many process measurements, the event is constantly varying. So only a relative few data are collected and available for the tomogram. That's why industrial process tomography compared to the medical process tomography is huge different in terms of the image accuracy, where process tomography is less accurate compared to the image that have been refined by the medical methods. So from now on, I will describe on the industrial process tomography, which consists of some listing here, which is optical, electrical resistance, microwave, ultrasonics, electrical impedance, electrical charge, and electrical capacitance. Okay, so due to the shortage of time, so I will discuss on the optical tomography, electrical capacitance, and electrical charge for the audience today. So optical tomography system, or OTS, is shown basically from this block diagram, where we applied optical sensors, okay, several optical sensors in dual plane over here. One is upstream and one is downstream, where we arrange such that these optical sensors have transmitters and receivers, okay, respectively, and projection of the beam of the optical sensors can be used as parallel beam or fan beam. So at the end of the day, the target is to collect the data when the particle flow inside the pipe, and this data will be captured by data acquisition systems, and then will be reconstruction using the algorithms for image display. As I told you before, for optical tomography system, we have two basic projections of the beam from the transmitter to the receiver. So the transmitter will produce the beam and the receiver will receive the beam. And this beam projection consists of two types. One is the parallel beam projections, where the number of emitter and receiver are the same, and the light divergence is not allowed. But for fan beam projections, the number of emitters and receivers can be unequal, okay? And then the light divergence is needed. So fan beam projection is much better, more recent in terms of parallel beam projections. So in early 1990s, the optical tomography is using a pin photodiodes, okay, where we have to arrange the pin photodiodes in the single plane over here, and there is an optical cable here which have a light source to transmit the beam from the transmitter to the receiver in order to obtain the image that cross the pipe in the process rig. So this is a process rig that we use, okay. There is a plastic bits inside here, will be sucked to the reservoir up here, and then will be dropped gravitically to the pipe, and then the sensors will be mounted here, okay. So after 1996, people are not using pin photodiode anymore. So people are using light LED, light emitting diode, okay, which is much better, more accurate in terms of data acquisitions, okay. So, and then with the LED, okay, we also associate it with the fan beam projections, which give better image and more accurate, okay, compared to the pin photodiode and parallel beam projections. So if you see here in this research project, there is a lot of hardwares, okay, a lot of hardwares involved, because when we design a tomographic measurements, the design of the tomographic measurements can be considered as one of the significant contribution in PhD or master's bar research. So in terms of that, embedded system for base solid gas mass flow rate meter using optical tomography also can be achieved, where we can measure the mass flow rate of the particular solids flow in this pipe, okay, and then we can use all the sensors arrangement and the signal conditioning using a digital signal processing system. So lately in the current research, so the parallel beam and the fan beam have been merged together, okay, which called as a mixed projections OTS or optical tomography system. All this effort towards the accuracy of the image that produced by the optical tomography systems. And lately, in the 3 years ago, bubbles have an issues, okay, where how to monitor bubbles that flow in the pipe, okay. So this is the content of a liquid, and the bubbles that inside the liquid, okay. So one of it is to use the optical tomography system, okay, and ultrasonic tomography system. So I will show you one of the design, a good design on the ultrasonic tomography system, which is using a sound, okay, that can detect bubbles inside the pipe, okay. So this is a real-time multi-phase flow for imaging system. So the flow is the bubbles, the liquid, and the gas inside the bubbles. So real 3D image, this is by simulation. You can see that bubbles that simulate okay, using the forward problems. And then this simulation will be verified by using the real experiment where we inject the bubbles inside the liquid. Okay. So this is the target of the image that we produce that show the concentrations, the distributions of the liquid, of the bubbles, and the gas inside the pipe. So the sensing mechanism that used is the ultrasonic sensors. Okay. So the arrangement of ultrasonic sensors is shown here using a sound. Okay. And some some of the publications. Okay. All these particular things. All right. So let's go to the other one. Okay. So CCD, one of the options for the optical tomography systems, which is known as a charge coupled device. So charge coupled device also is one of the research that under our group, okay, where we use the charge coupled device is the integrated circuits containing an array of link or coupled capacitors. So under our control of an external circuit, each capacitor can transfer its electric charge to a neighboring capacitor, which used to capture the digital imaging. Okay, so this is one of the options of the optical tomography system. Beside using pin photodiodes, beside using LED and so on. So the next mechanism of process tomography is known as the electrical capacitance tomography, which is this capacitance sensors is measure the changes in the capacitance from the multi-electrode sensors, which is shown on the left-hand side here. Okay, and then it reconstruct permittivity distributions, which is the image, using a measured capacitance data. So electrical capacitance tomography, or ECT, is a technique to visualize the distribution of two dielectric components, which measure the changes in the capacitance or the permittivity by using the formula C is equal to K epsilon, where epsilon is the permittivity and K is the constant. So instead of static design, okay, the research group come up with the ECT mobile sensor design. So previously in the research, the capacitance sensor is fixed. Okay, the tomographic measurement is not mobile, it's fixed to the pipe. But now the design become more handy, more portable, which is a non-destructive, non-invasive, and non-intrusive sensor, and can easy assembly on the pipeline. Okay, so this is the hardware design of the ECT electrical capacitance sensor tomography, which using a capacitance sensor over here, which can be taken out one by one. Okay, easy to take out and replace if it's not functions, and then using a central control unit for data display. So ECT hardware system consists of excitation electrodes and receiving electrodes, where the red one is the sensing electrodes and the yellow one is the grounded screen. Okay, so this design of mobile ECT is one of the point that attract the attention of the industrial practice outside there. Because due to the fact that this ECT is capable of detection the water, the oil, and the air, okay, which known as the three-phase flow visualizations. We know that water, oil, and air cannot mix together. So this ECT mobile is able to show the image of the air, of the oil, and of the water levels using the ECT technique. So it consists of two-phase flow and three-phase flow, either is solid and liquid, or solid, gas, and liquid plus oil together. It's also capable in measuring the velocity profiling. Okay, so in order to measure the velocity, the design must have two stages. One is on the upstream sensors, one is on the downstream sensors. Okay, and then this distance between two stages is known, and then the transit time between the upstream to downstream is known, so we can know and found the velocity by taking the distance divided by time taken for the particle to travel from upstream to downstream. So the next one is I will describe on the electrical charge tomography, which is shown here. So electrical charge tomography is using the very basic formula in physics, where Q is equal to CV. Charge is equal to capacitance multiplied by voltage. Okay, and this concept been applied in the circuit here is known as the electrostatic sensors. Okay, so this is the sensing part, which is the metals, and this is the output of the sensors. And this sensors was designed particularly, okay, using a smart PCB design. Okay, and this electrostatic sensor will put around the pipe, okay, in order to detect the movement of the solid pipes, solid pipe in the gas. Okay, so data captured, which signals detections is shown here. Okay, the yellow is the voltage signals, and the turquoise color is the inductions voltage. So electrostatic sensor is using a moving dielectric object in the air, okay, where you have a particle movement, solid particle movement, or maybe it can be a plastic bits, or it can be anything solids that crash together, moving together and crash together, they produce electrostatic charge. And this static charge will be detected by the electrode design in the yellow part, covered by the insulators, and the voltage from the sensors here will be captured by the data capture system for further processing. So for electrodes in the electrostatic sensor, it depends on the pipe. Depends on the pipe design. Okay, for example, in the industrial, they are using a circular design pipe and the square design pipe. If the pipe is circular, so we are using the isolated ring, isolated arch, exposed ring, and exposed arch. This is all the sensor design for the electrostatic sensor. Okay, so is it intrusive or is it non-intrusive? It depends on the design here. So if you see the E, here is exposed isolated rod is considered as intrusive design, where it goes inside the pipe and it will disturb the flow inside the pipe. Whereas on this one is isolated ring is considered as a non-intrusive design. Same goes to the rectangular pipe. Okay, sorry about the title, it's a rectangular. Okay, so if the rectangular pipe, you have a design of single square, quadrilateral strips, 3x4 strips, and 3x3 strips, which is the front line of the electrostatic sensors. So in electrical charge tomography system, research mainly on to produce a concentration profile, velocity profile, mass flow rate profile, solid particle sizings, sensor design optimizations, and flow regime identifications. For example, if you want to measure a velocity of the moving solid particles in the pipe, we place the two sensors here, which is upstream and downstream, okay, here. And then we capture the data of the voltage on the upstream, data of the downstream signals, and then these upstream and downstream will be cross-correlate together, okay, to find the similarities between two signals, between upstream and downstream. And these similarities are represented by the peak value of the cross correlations, which detect the time delay of the transition time, from the upstream to downstream. As long as we know the distance, L, so we can find the velocity, which is L divided by the tau, which is the time delay, which is the time taken from the upstream to the downstream. So in this electrostatic sensors designs, electrostatic sensor research, we also considered the particle sizings, okay, to be investigated, okay, using a process jig here, where we can detect several particles, okay, vary from 5 millimeter to 1 millimeter. So the electrostatic sensor is able, okay, using the electrode design here, to give the value of the particle size of the solids in the pipe. The other research also is on the image reconstructions. So if you see this drawing, so we assume there is a particles flow here inside the pipe, a solid particles flow, and then we try to design a new image reconstruction algorithms, okay, using many methods. Okay, one of the method is using a finite element. One of the method is using recursive least square regularizations and other methods. And then this algorithm will be verified by using a CCD camera. Okay, so CCD camera is the real measurements. The image reconstruction is the simulations measurements, and this will be compared together. Okay, so this is the real part of it, the real plan of it, where we put a camera over here and the flow is over here. Okay, we are using a electrodynamic sensor or electrostatic sensors, and then compare with the CCD camera image in order to find the new image reconstruction algorithms. Other research in electrostatic sensor is listed here. Okay, image reconstruction using least square with regularizations, using a finite element method, particle sizing, and optimizations of electrostatic sensors. So other sensing techniques that I will not describe is including the magnetic induction tomography, ultrasonic tomography, electrical resistance tomography, and gamma ray tomography. So in 2010 onwards, the research in tomography has been expanded rapidly by introducing a dual modality techniques. Dual modality technique meaning that two sensing mechanisms are combined together, consolidate together in order to enhance the image that shown, the image they obtained from the measurements. So they are using ultrasonics and electrical capacitance tomography, and ultrasonic and electrical resistance tomography. This modality technique is vital due to the fact that one sensing mechanism have their own strength and have their own weakness. Okay, the weakness of ultrasonic is covered by electrical capacitance, and the weakness of electrical capacitance is covered by ultrasonics, in order to enhance the image by fusing the data from the ultrasonic sensors and electrical capacitance sensors. Ladies and gentlemen, now I'm going to the part 3 of my presentation, which is research in the system identification and estimations. So system ID is one of the topics in the control system, is related to the mathematical modeling, building mathematical models of dynamic system based on the set of measured stimulus and response data samples. So system ID can be applied in wide range of applications: mechanical engineering, biology, physiology, meteorology, economics, and what I'm focused now is on the model-based control design. So let us see that mathematical models is around us, okay, is a real-world system, which is difficult to build based on the first principle alone. Sometimes it's not easy to derive a mathematical model based on the first principle applications. For example, using a physics law, using a chemistry law, and so on. Okay, so one of the methods available and which can be used is the system ID, which is known as empirical modeling. We are captured data from the input and the output, and then we build the model based on the input-output measurements, and we let the data speak about the system, the real behavior of the systems. So the main objective of the SI or system ID is to obtain a parsimonious model, okay, that adequately representing the system. So what is a parsimonious model? Parsimonious model is a model with a few parameters as possible, which give a good quality of a model. Okay, so when we said about system ID, we are talking about the structure, the model structure, the model parameters, and the disturbance that involve in the system. So if we see the spectrum of the models, okay, so system ID is about building the dynamic models. Therefore, some knowledge about the models is necessary for successful identification process. So I can say that if you know nothing about the system, you don't have any idea about the system, or no information about the system, so you are blind and you are dealing with the black box where you don't have anything, any idea about it. But if you have some informations, some formulas, some components that you know inside the system, so that considered as the white box. Okay, so it vary from the black box to the white box. So usually in engineering is in the middle. Okay, the gray model. Okay, between black and white is gray. So gray model is the model that involved in the system in engineering. So you can see that in the black box model is psychological systems, social systems, and it can be economic system as well, because we don't have data in order to speak for itself. So system ID is a general term to describe mathematical tools and algorithm. So we can consider it as the three box, which is a white box, gray box, and black box. So black box, you know nothing, you don't have any informations, but white box, you have some informations, detailed informations, but gray box, you have half, 50% knowledge of the system, and the remaining 50% is unknown. So which one is better? Is it modeling using analytical or modeling using empiricals? Analytical is by derivations, by using mathematical models, derivations, using a physics law, using a chemistry law, using the circuit theory, and so on. But empirical is you just inject the system with the signals, the excitation signals, and then you capture the output, and from the input-output data, you will get the model. So how do we obtain this model? It's simple as here. So which one is good, which one is bad? So both are good. Okay, so physical modeling have their own pros and cons, which physical modeling consists of modeling a conceived system before hardware is built. But in black box, you don't have to build the model. You just inject the systems, okay, close to the actual input-output behavior. It's a convenient structure for parameter tuning, and useful for complex system too. But both of them have their own disadvantage, okay. For example, in physical modeling, is often lead to the high system order with too many parameters. It becomes complicated. Okay, but for the black box, no direct connection to the physical parameters, no solid grounds to support a model structure, and not available until an actual system has been built. So both have the pro and cons. So it depends on the engineer, it depends on the researcher. Both methods are good. But if you choose to use a system ID, so the procedure, you have to follow the procedure. First is you have to design the experiment. Then you have to design the model structure. So if you see the model structure, it can be linear, it can be non-linear. Okay, so if you choose a non-linear model, so the model will be more complicated. Then you have to estimate the models. Then you have to validate the models. After you estimate, then after you validate the model, so is it the model accepted? The model accepted is depends on the accuracy, okay, the accuracy percentage, okay. of the models. So usually we are using more than 90% accuracy, then the model is accepted. Otherwise, it will repeat again the experiment, it will repeat again the model structure selections, it will repeat again the estimated models method that we use and the validation model that we use. So I can say that the experimental setup, in order to obtain the mathematical model of the system, is shown here, where you have to design the experiment and you have to design the signals, the input signals, and this is the unknown plan. And for the research here, the significant contribution for the research is at the identifier algorithms, to how you estimate the mathematical models and the parameters. So this is more, if you go to the research in the control system, so the identifier algorithm is vital, is the important, is the method that always change very fast, dynamics. Okay, every day people producing a different identifier algorithm in order to produce the good models. So I will show you the gray box here, one of the sample of the gray box, which is using the hydraulic actuator systems. So this system is the EHA system test bed, is in the laboratory, process control laboratory, where we have the cylinder of actuators, and we have the external disturbance. We have the accelerometer to measure the motions of the load of the pistons. Okay, we have the pressure sensors on the left and on the right. And basically, in this experiment, we are trying to detect the position tracking of the pistons, okay, that bring the loads over here. Okay, so position tracking. So in order to measure the position tracking, we need a displacement sensor, which is the draw wire sensor. So this draw wire sensor is a sensor that detects a physical signal, which is the displacement, and then it convert to the voltage. Okay, so we also can use LVDT, okay, linear variable differential transformer, as an options. So this process, okay, have a oil liquid inside, okay, which pumped by the motor, and this piston will move to the front, to the back, and then we need a power supply, because draw wire sensor or LVDT is the passive sensor. It needs a power supply in order to operate the conversions. And then we capture the data, okay, using a computer and data acquisition system. And then from the data, we produce the nearest mathematical model that represented by the hydraulic actuator system here as the gray box. Okay, so this is the component in the hydraulic actuator systems: the pump, the servo valve. Okay, so actually we are controlling the servo valve, the door of the servo valve. Okay, the opening of the servo valve that control the liquid flow inside the hydraulic actuator system. So I will show you a video. Sorry if it's quite noisy. Sorry. So this is the video shown here. The piston is moving, okay, from front to the back. We are using LVDT to measure the displacement. The input signal that used is the sine wave, okay, and the output signals that captured also sine wave, but different in terms of magnitude and phase. So monitoring of the signal input and output using oscilloscope, and will be capture the data using data acquisition systems. And then this is the process the data in order to build the mathematical model. So once the data, we capture the data, okay, so it will be here, the input, which is a sine wave, okay, so sorry, as a cosine wave, inject to the plant, and this plant will be estimated by the adjustable discrete time model, the estimated model, okay. So this model is come from the parameter adaptation algorithms, okay, that adjust the parameter value so that the parameter value will be as close as possible to the plant. So this is the input data. So I show some examples here, which is sampling at 45 milliseconds. Okay, the input and output data. So if we captured 1,000 data, so we divide the data into two parts. One is the first part. The first 500 is for the estimations. The remaining 500 is for the validations. Okay, so after we process it, so we use the model structure selections. So in these selections, the researcher must be very careful either to choose the linear models or the non-linear models. So let's say we choose a linear model, which is ARX331. So this model is a third order systems, okay, because this system is known as a third order. And then we analyze the poles and zeros of the data in discrete form. We have a 3 poles and 2 zeros, and then you can see that the plan and the models, the accuracy here, okay, the accuracy is about 94%, okay, which is mean that the model follow the plan 94% accurate. So model you can consider as estimation, and plan is the measurements. So the simulation and measurements, the accuracy of the output is about 94%. Okay, 94.6%. Okay, and this is supported by the loss functions, the FPE, and the archive case information criteria. Okay, so based on the smallest value, so this model is accepted 94.6% because the theory said that the acceptance of the model is more than 90%. So this is some of the topics that I offered, the group offered for the hydraulic actuator system in terms of the modeling and the controller design using a mixed backstepping with optimization approach, using a fuzzy approach, using adaptive sliding mode control, and control and optimizations of electrohydraulic actuator system with a mismatch disturbance. So the second part, the second gray box here is the pneumatic actuator system. It's quite similar from the hydraulic actuator system. The difference is the medium, where the hydraulic actuator system is using oil, but in the pneumatic actuator system, we are using an air, okay, as the medium. So this system consists of a valve, control valve, magnetic sensor to detect the displacement, a pneumatic cylinder, loads, compressor to compress the air, and the DAQ to capture the data. See, this is the main component of the systems, okay, which is the control valves. What we are trying to do is to model the system and then to design the controller that control this control valve in order to the output will follow the input. I'll show you some video of these pneumatic actuator systems. So this is the load, okay, of the pneumatic actuator system, and this is the piston and the pressure sensor. The black box is this box with the control valve, two pressure sensor, inlet and outlet. And it goes with the magnetic sensor to detect the position tracking of the piston that carrying a load. So the magnetic sensor is shown behind the load there. Okay. So this is the magnetic sensor. all the data will go to the computer for processing in order to produce the accurate model. Okay, so this is some of the topics in the pneumatic actuator system in system ID estimation and control design. So we focus on the dead zone problems. So we focus on the enhanced nonlinear PID control algorithms, and then using a nonlinear gain constraint model, predictive control, or MPC. So now I reach to the part 4 of the presentation, which is to highlight the other research activities and opportunities in a PROTOM-i group. Okay, so Professor Rosari offered a new vacancy for the PhD students, which involve in the UTM CAPS drone. Okay, UTM Campus Autonomous Patrol and Surveillance Systems, where Prof. Rosari is the program leader and is the project leader number 4. So those postgraduate or future postgraduate students that have an interest in drone design can report to him and email to him. And by myself, I have 2 current research grants on the flow regime identifications, okay, in solid particles moving, and then particle sizing measurement using electrostatic sensors via spatial filtering effects. Okay, so I offered a 2 place for postgraduate students, one for the first grant and the other one for the second grant. 2 PhD students are needed. And then the third one is I want to highlight the Microelectromechanical Systems, or MEMS. Okay, and as I said, Prof. Engineer Dr. Sultan Muhammad Ali. Okay, because his research interest is on the macro actuators, wireless device, biomedical device, energy harvesters, and micro machining technologies, which is shown here. The current projects is using a wireless MEM. Okay, SMART stand for angioplasty. I think this wireless MEMS dielectric elastometer macro actuators. So Dr. Sultan give opportunities for masters and PhD research student to work with him, okay, under this project, MEMS project. The fourth researcher in our group, Dr. Herman Wahid, is a PhD holder in artificial intelligence. Okay, so his field is AI, applied control engineering, environmental instrumentation and prediction, and energy harvestings. All correspond to the applications of artificial intelligence. Currently, he have 2 research grants to be offered for postgraduate students. Okay, those who are interested can communicate with Dr. Herman. The 5th researcher that in my list is Associate Prof. Dr. Leo Peling. This Dr. Peling research interest is in sensors, actuators, instrumentation and measurement, lab on chip, okay, and microfluidics, okay, in the micro scale and in the nano scale, okay. So Prof. Dr. Leo Peling have about 3 research grants available for students to enroll as postgraduate students. Not to forget our Deputy Director of RMC, Associate Prof. Dr. Herlina, also available to be your supervisors in the research expertise of instrumentation system, sensor technology, near-infrared spectroscopy, okay, and optical tomography. And Dr. Shafis Suhaza Sahlan, also involved in the control and automations, energy management. Okay, she have 2 grants, research grants, actively, and those who are interested in this field can communicate with her. And Dr. Hairul Amima Abbas, also one of the members, have a research interest in image processing, signal processing, membrane electrical properties, membrane structural imaging. Okay, she have one research grant and student available for PhD and masters by research. And another one is Dr. Jesuman Puspanathan. So Dr. Jesuman Puspanathan is not from electrical engineering. He's from School of Biomedical Engineering. Okay, but he is registered under our research group. His field of interest is tomography for process industry, drone technologies, sensors, actuators, and he have one research grant available for postgraduate students. Dr. Yusri bin Yunus, also one of the members in the PROTOM-i, offered a UTM grant, investigation of an acoustic technique to monitor insoluble substance and bubble forming in clear juice fruit processing line. So he can be contacted because his research interest in the optical sensors and tomography. And not to forget acknowledgement to the guru which inspired the group PROTOM-i, Professor Emeritus Dr. R.G. Green, okay, from Sheffield Hallam University, UK. His idea, his comment, okay, advice have made PROTOM-i one of the significant research group in the School of Electrical Engineering. Thank you, Prof. And to conclude my presentation today, I have taught 4 parts of lecture. Sorry to keep you waiting, it's about 1 hour. Okay, so part 1 I talk about the introduction of the research group, the process tomography systems, the system idea and estimations, and the research grants and opportunities available for the students. So those who are interested can join our research group, okay, to further studies for masters by research and PhD by research. Okay, so all the best for the future candidates, inshallah. So that's all for my presentations. Okay, I pass to Professor Kamal for the further presentation. Thank you very much for listening.
Okay, thank you very much, Prof. Fua'ad, for very informative about sensor actuators about your research group. And now I would like to open for any question and answer from the viewer from this FB Live. If you have any questions, you can post throughout the comments of your Facebook, and I will read the question. Maybe 1 or 2 questions. Okay, maybe I can ask you one question, Prof. Fua'ad. Can you name a few companies in Malaysia, basically, that will be interested in this process tomography
All right.
research? Any companies that, very interested in this
Can you
area?
show the slide, Prof? So
Huh?
can you show the slides if you don't mind?
Yeah.
Slides. So companies engagement in the research. Basically, we have about 4 or 5 companies. Opto-Sensors Malaysia Sdn Bhd used to be, now is Osram, Opto Semiconductors.
Okay.
Last time it was Opto-Sensors. They changed the name. So this Osram Opto Semiconductors have sponsored our process rig in the process control lab. Okay, so we are working together on the optical sensors last time. And then not to forget is MPOB, Malaysian Palm Oil Board, which is a government agency. This project related to the electrical capacitance tomography and electrosonic tomography. And then Malaysian Nuclear Agency also involved in our research group. Okay, and then iStone Technologies and Rahmat also involved in our research group in terms of doing the hardware and marketing the hardware.
Okay, all right, thank you. Okay, just another one question with me. Which method of modeling is accurate? Whether is it analytical or in terms of empirical modeling? Which one do you think that is accurate?
As to be frank, both are good. Okay, so analytical modeling need derivations. You need knowledge, highly knowledge on the mathematical models. You have to understand the principles very, very deep in order to derive the accurate mathematical model. So this will take some tedious step, very details, okay, very complicated derivation in order to find the mathematical models. But in order to have a, what do you call that, alternative, okay, so System ID offered alternative, which is known as empirical modeling. So you assume the unknown system as a black box or a gray box, then you inject the system with the test signals, and then you capture the output, and then you process the data in order to produce the mathematical models which really describe the behavior of that particular systems. So usually researchers are doing both the analytical and empirical modeling, okay, and they compare together to make sure that the model they get is acceptable and accurate.
Okay, all right. I think that's all for today's event. Once again, thank you very much to our Professor Dr. Muhammad Fua'ad Rahmat, the head of Process Tomography and Instrumentation Research Group. Now, I would like to pass over to Puan Sherry for the closing remark and for our next week's event of this webinar series. Over to you, Puan Sherry.
Thank you, Prof. Kamal. And thank you also to our guest speaker, Professor Dr. Muhammad Fua'ad Rahmat, for the interesting topic just now. Thank you, Prof. All right, viewers, we are at the end of our session today. Thank you all for taking out time to watch this live telecast. And for those who missed this live session, can watch the video again in our Facebook. Don't forget to like, comment, and share our Facebook and videos to your friends and colleagues. And please don't forget to join us next week, 8th of September 2020, 2:30 p.m. for the next series of webinar with our guest speaker, Dr. Noor Asniza Murad, the head of Advanced RF and Microwave Research Group, on the title of Research Trend in Microwave and Millimeter Wave Devices. Alright viewers, as usual, I will end this session with a quote. Umbrella can't stop the rain, but can make us stand in rain. Confidence may not bring success, but gives us power to face challenge in life. Okay, dolls, smiles a lot. It's free therapy. See you all next week. Stay safe, keep your distance, and stay tuned. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.